record this so that, because it's hard to listen to, I think, in a consistent way. So we have a program here. Which looks like not the one. Oh, here it is. Yes. Okay. It is the one. Because we have the function header up here. We have the function down below. We have the main method. All it does is calls the function and saves the answer and then returns it on the command line. We saw that that works. And then the function f just adds up the integers 1 through n. So like we know that the answer is going to be, well, we expect the answer will be 55. If you put it 100, it should be 5,050, but that probably won't work, might not work here because that might be too high a number for the 1 byte that, for the int that gets returned there. I don't know what would happen if you put that. We could try it and see. And here's the loop. Here's the function rather with 2 local variables, a sum and I. And there's the 2 local variables here. So I was commenting on the activation loop here, and we were looking at how the loop was implemented. So we saw that first to sort of isolate the part of the code that corresponds to line 16 through 18, the for loop itself. You can look at, here's the activation record, here's the code that runs F. It's the sets up the activation record by and large, and has the code that implements the body. So this first bit here in line 9, we see that F has 2 local variables. There's the 2 there because this is the final movement of R6 to hold the address of the top of the stack. And we know that R5 crosshatch 0 holds the variable I, and R5 minus 1 holds the variable sum. So the assignments here are in the same order that they are in the program, as they have to be, but the location isn't like first you come to sum that would, so it's switched from your normal expectation of what memory cells are being used to hold sum and presumably that has something to do with the fact that this has an assignment and this is unassigned. Okay, so basically line 14 here ends with line 13 here, right? So starting from line 14 onwards, we have the loop. And if you go down to the bottom, you can see that this line on line 47 here reads a variable from R5 minus 1, which was the variable sum. So this is the return code marked by L10 here. So, and the structure of the loop was, let's go through. First, it has to do this evaluation of whether you should run the body of the loop at all. So it does I equals 1. These first 3 lines are just the assignment for I equals 1, okay? Rather, I think that's incorrect. This, well, no, it is, let's see. Yes, I think that's, well, actually that's incorrect. This is, well, no, it does set I equals to 1. So we have done this first thing there. We set the initial, we've initialized that. So that sort of puts together, you know, you had the int I up here, but you have the I equals 1. So this is as if int I equals 1 was the instruction here. Okay, so whether it's in the loop or not, we can include it with we should probably include it with a loop. Okay, what is this first bit? Well, if you look at the jumps here, this first bit, R4 plus, gets the address of L8. And L8, if you look down here somewhere, is let's see. Oh, there it is. You have to, it's like the LC3 underscore and the name of the program is sort of hiding the line, these line number, the ones that you want, the reference number is L8. So you can just, we're just going to identify them with that. So it's easier. Okay. Well, this is the targeted decision. So that jumping here jumps over what's going to be the body. Okay. This is the body of the loop here. So it goes to the decision in which this loads the one that was written up here, because it's doing this comparison here, loads the one, okay, into R7, loads the parameter value. That's why you have +4 here. We were looking at yesterday at the activation record here that R5 points here to the first local variable, 3 bookkeeping, and the parameter n. So R5 plus 1, 2, 3, 4 takes you to the parameter, which is here. And then, no, I'm sorry, it's R4. This was R4 plus 4. I get confused. This is R5. We're down here. R5 plus 4 is the parameter value, 10, and it's going to make -1 from the R7, then add R7 and R3. So it's calculating n minus 1 is greater than or equal to 0. And if this is negative, that is if the -1, if n is not, if n minus 1 is negative, because what's going to happen is that I, which is the 1 here, is going to get larger and larger and make this n doesn't change, but I will change. And when it gets to be 11, because it's going to be increased over here, it'll become negative and you'll branch out of the loop. So assuming you don't branch out of the loop, then you are going to you're going to fall through this branch and get to the 3 instructions that take you back to the target. It does it this unwieldy way of getting the address up here, the address of the address, then this is sort of the address. This is one of the, the address of L5. Then this next line here is the address of L5. Okay, and then you actually jump there up here. So, and this is what we got to at the end of class on Friday, where we start with the body here, because we're assuming that this was positive, that this was satisfied. So it does this first, then the condition, then the body. So it loads R5 minus 1. R5 minus 1 is sum. Okay. And what does this next line do? It loads R5, R7 equals sum. R3 equals I. So it's loaded sum and I. Then R7 equals sum plus I. And then this is stores. It is sum equals R7, which equals sum plus I. So this implements the body. So this is these 4 lines are the implement the single line of the body here, and that's interesting in itself. Because this is one of these increments where you've incremented a variable, so you load it, add one, and store it back. Okay, what happens after you've completed the body? Well, you should then we need to increment I, then go back here and check again the decision. Well, the decision's already down below, so if we just increment I, the decision will be down below, and then we can continue just falling through. Okay, what this does is this loads R5 cross that 0, so that R7 equals I. Then R4 plus 7 is in the global variable. R4 plus 7 is 1. So this is R3 equals address of 1. R3 equals 1. Then R7 equals, what's R7 plus I3? R7 is I, so R7 equals I plus 1. So I plus plus as short for I equals I plus 1. In other assembly language routines, this may be done in a more efficient way than this sort of procedure here. Okay, then I equals I plus 1. I equals I plus plus. So this is the increment. So we do the increment, then we just fall through. That's one reason to put the decision down here instead of putting the top, because then we fall through and make a decision. We've increased I, so we make the decision down here. We could make this as see, R7 is I. We could leave this as, maybe better put this as I. I is there so that you've incremented I, it's gotten one larger, so it's possible. So then you decide, and so we've done if you go back over, but if you exit, what happens if you exit? You jump to, you fall through, right? What happens if, oh yes, so if you exit here, I mean, you've come through, if you come down here, you're jumping back, but if you branch here and this has become negative, then you branch down here to L10. This is have jumped out of loop. Okay. So, and then you're back to the return. Now, one thing we haven't done before is to see what happens when you return from a function, because we've done the loop now inside a function, but then we come up here. So, because let's first look and see what gets torn down, because the activation, part of the activation record gets torn down as you leave the function, because this has to get restored. So let's see what happens as we tear down this stuff. Okay, well, you R6 here equals R5 plus 1. What does that do in terms of the activation record? Well, R6 is now up here. Let me make this red for going up. R6 is up here. So if I set R6 to R5 plus 1, then it goes here. So where it points to is mains R5. So this then takes what's in that memory cell, R5, then equals mains local variable pointer. It's local frame pointer, okay? So this is the line 53 here, that deallocates all the local variable memory. Because when you add something to R6, you're deallocating memory. So when it asks you on regx what deallocate, this is the line here, or the analogous line that deallocates all the local variables. Okay, this then, the next line here does some, it says R6 equals to R6 plus 1. moves it down one space. Well, R6 plus 1 means that it hops from this is the first local variable for R5. That's now been removed because now R5 now points here to main's local, which is answer, right? The first local variable of main. And now then R6, so this happens first, second, then third is that R6 now points to the return address. R6 now points to return address. So that we don't know what that address is, right? However, it's going to be this line here. So we have to go back to our main things. So it's going to point to the return address. It's here. Let's see. Let's find the function call. Main. Here's main. Oh, it's not okay. Here's the function call. So return address should point here. The return address should point to wherever address line 35 is at. And we could calculate that, but that's not the important thing. Okay, so then we set R7 equals return address of line 35, as long as I don't add any lines to that file, of line 35 in main. Okay. Then finally, R6 equals R6 plus 1. What is that? That is then over here in the activation record. R6 goes here. So that 3 is here, then R7 is set. So it doesn't set the activation record, but R7 is 3, 4 is set to address in main to return to. Then you move R6 is here. So R6 now points to the 10, right? Which is the parameter. No, actually, I jumped one. Yes. Let me see if I can recover this. We got the return address. We did that. Then we added 1 to get here. So I jumped 1, unfortunately. I jumped 1. R6 now points here for 5 to the return value. That's important. R6 points to return value. Which is up here, okay? Now, let's see, what is the return value? Well, in the F activation, right? We have, that's the question is, where did we missed one. Yeah, here it is here. Line in F, I forgot to do one thing or mention one thing, was that R5 minus 1 has sum. We've read the variable, and this writes the return value. So, for example, we have now the 55 here. So R6 here points to the return value of, which is here 55, if n equals 10. So you've got the return, then it returns, and we're back here at this line here. Okay. So since you've returned, it right away reuses R7 and gets and puts R7 equals R6 plus 1. Well, that equals the return value, 55. Let's got this too long a line. Okay. Let's make it shorter. Okay, return address points here. So when it's executed, it sets R7 to the return value. Okay. Then here's the final R6 equals R6 plus 1, which moves. So now after the jump, 6, R7 equals 55, return value. And then R6 is jumped again. You see R6 equals R6 plus 1, right? So it equals the parameter 10 here again. I'm missing one. Let's go back and see. Oh, yes. I may have missed one R6. Let's see. This one definitely writes the return value R5 plus 3. This sets R6 to be the return address. This sets R5. Then we do this sets the return value here. This stores that return value. Then, oh, so this points, yeah, this is, we've just written the return value. Okay, I've gotten this. Let me just redo this to make sure that it's clear, at least in my mind, so we can sort of proceed with this, because we want R6 to point to the top of the stack, so that we have R6 points here. That's first of all. So put a dot there. This is where we are here. Okay, thanks for bearing with me. We've set R5, then we move R6 down to the return. No, this is the first one. R5, R5 plus 1 is up here. This one sets it to the return address. This one sets it to the return value, okay? Then we've got R5 plus 1, we've got R6 sets yes, I was right before, R6 to return value, okay? Then here we've returned and we've added 1 to R6, so that R6 equals, looks like parameter address. Okay, then what do? We store R7, which has the return value in mains R5 minus 1. So this sets mains R5 equals to return value 55. So this then gets copied because it was stored in R7 and then it gets put there. So now that's completed this line here. We've completed line 6 in the program. Okay, then we come down and this starts to return because R7 equals, it loads what's in R0. That's the 55, right? So it's loading value in answer. Then it sets return value because R5 plus 3, 1, 2, 3, it sets the 55 there. Then this is doing the analogous thing for main. It sets R6 to R5 minus 1. So the fact that here R6, when you came back, pointed to the parameter value on the top of the stack rather than to the previous top, which was the local variable. Okay, so that's it. That's basically, so you can see that what it's doing is you can think of this whole thing packaged together as a stack of activation frames, which although it's the details are messy, it takes each activation frame and puts it on the stack and pops it off the stack with exactly the same code. Although the details of this function call seem like maybe overly tedious or difficult or sort of like complicated to sort of get a hold of, they're the same for every function call. So it doesn't matter. It's like if you do it for one function, you'll do that. It'll be the same stuff for all of them. So once you understand that, you can take the picture of the activation code and then analyze what is happening inside the C code, just looking for separating off the function call from the loop itself or the bot, whatever else it's doing. Okay, so that's taken a while. Just a second, let me. Okay, the door was open, so I just closed it because I could hear the voices outside. So if that was getting recorded, then might be annoying.
We didn't hear it, but thank you.
Okay, just in case. Well, good. I'm glad you didn't hear it. That would be a good microphone on my computer's part if the built-in microphone could pick up very low chattering in the hallway. Okay, well, that is the stuff with it's a lot of stuff just to analyze. So, but the point is though, you can ask, well, why are we doing this? What's the point of doing this? And the point is that you're used to looking, now this is low-level code compared to Java or Python, but because it's very close. Now, if we looked at the real assembly language that's going for this, it would be more complicated, but it would be very similar in spirit. And so it would be what's actually going on in some sense, is the assembly language. That's why, for example, a lot of malware and other things or issues that occur at the level of assembly language, because that's where stuff really is happening. It's sort of like all the high-level languages, you know, are sort of like on the surface of the ocean, and everything else is being fought underwater, like with submarines, right? If you think of assembly languages like submarine stuff, okay? So the problem is then that it also helps you to write more, not only that, but it helps you to write more efficient code if you realize that something is happening, that this is like a piece of theater. In terms of the hardware, any programming language is a piece of theater. You have an image, just like you go to, say, a play in the theater and you see the actors moving around and saying stuff, and it gives you the illusion of that story taking place. Here, you have in your mind a story of what's happening in C or Java, and that's really not what's going on. It's a piece of theater. Behind the scenes, something else is going on, and in many cases, you need to know what that thing is in order to write efficient programs, or to understand why certain devices, or certain things happen in, make things slow or fast. Although not relevant here, for example, you might think in mathematics, you could take one loop and put it inside another loop, as long, and then, and reverse the order, do one loop. If you had a double loop, you might be able to do double loops in either order. Well, it turns out that if you're dealing with arrays, like double arrays, then one order could be much slower than the other order, although mathematically they're identical. And that has to do with the way that your memory organizes reading the numbers from the array. And that has to do with how data structures are stored in memory. And so there's courses and books that deal with this stuff. There's a book at sort of the next level up from this course, which is, in fact, let me see if I can find that for you, because it's really sort of the computer systems. Oh, a programming. I think this is it here. Okay, it's Computer Systems, a Programming Perspective. And I don't want the publishers, though. Let's see if I can get. Once. Yeah, let's just find this. Okay, here's the, they're not going to give us I wanted to look at the table of contents, but this text does what I was just mentioning, and it's used to, it's sort of like a nice reference book that does this, and you can find earlier editions online, but some of them are 32-bit and some of them are 64-bit. And I think if you can get one of the older ones, even if it's like, as long as it's 64-bit, but any of them, even if you can find one for much less cost than whatever this one, you know, $116. Oh, the hardcover, the paperback's only $30, right? So I'd recommend this book because it goes over, and it's written from a programmer's perspective about architecture. So it's doing the same stuff we're doing. Maybe I do need to go to the publisher to find, I want a table of contents. Because I've got too many. Let's see. Okay. I want, Oh, here it is, table of contents. Okay. Representing manipulating information, machine level representation of programs. This book has assembly language. It covers assembly language here. Then processor architecture, optimizing program performance, and the memory hierarchy. It actually tells you how virtual memory has hardware support for being translated to physical memory. Okay, which is which is really important. And then there's other stuff here that goes on in it. Anyway, all of these topics deal, like your system calls. So it deals with basically all the stuff in our CS214 and CS212, systems programming in C, sort of at a next level up. It's like a junior level course in, it's designed to be that kind of course. Okay, but I recommend it because it's only $30 and it's a good reference course, a reference book for looking up this kind of information and giving you a sense of why what we're doing here is relevant and worth the trouble of learning this sort of stuff. Okay, other questions? Excuse me? Yes, well, I'm sure that there are, online, there's all kinds of versions of the earlier editions or whatever. Anyway, so that looking at it is a worthwhile sort of background. It's much more detailed, and it doesn't deal with like LC3. It goes straight to the real assembly language and teaches you about programming that. And okay. Oh, yes, yes, okay, we'll talk about something else later. Anyway, so so we have a for loop, right? And about 10 minutes left. Let's start to look at, that was, oh, no, we can do cancel. Let's just add a function down here, int, let's try w int n, in which what we want to do is perform the same task, but use a while loop. Okay, so we're still going to need a sum variable, right? And maybe we'll need that. Let's look and see. While sum, no, we need the variable I, right? Int I equals 1. And we have while I is less than or equal to 10. We need to do sum equals sum plus I. And then I plus plus. Let's try and make it. And that's it, right? That's going to, because it's going to be less, I is less, not less than 10. It's less than n, right? So we have the same thing, I less than 10. We have the int I equals 1 first. So you notice the int I equals 1 is going to occur first in both of them, even though as a convenience is put here. And then you do, and then this is for this, anyway, is just, so the for loop and the while loop are really equivalent. They're just organizing this and this differently. So we wouldn't expect much difference between the while loop and the for loop. So it might be a little bit difficult to distinguish them. Okay, but that's the same thing. And we can then type make, and I have an error. let's see. Oh, let's see if the problem was the header or maybe the LC3 compiler. I haven't tried this before having multiple functions. Maybe the LC3 compiler can't handle this. Which line? Oh, unrecognized declaration on line 37. Oh, I have an extra, there's the point. I have an extra here. Okay, that works. Now I want to save this as, this is going to be forloops.asm. And that's still okay because this is just, okay. But then we should be able to open. Now, I didn't call the function, I just did it. Well, let's just see what happens. Okay. Oh, I already have that. Open in the other one. Open loops.asm. I saved it up here. So here's the loops again. There's main, there's F, and there's W. One can sort of hope that F is the same, right? But it might not be. Let's see if it is. Oh, let's. Well, I've done some editing. And the numbers of like, here, well, how is it going to be different? Well, it's only going to be different, I think, because this, oh, wrong place to do that. Here. This number is 6 and this is 10. So the global variables have changed because you've got more global variables. But otherwise, here's 11. So otherwise, I think, apart from my introduction of spaces, this should be identical for F and that. But then we have a new function here, W. So we have the same. And if we compare it to F, right? Because although it's W, we can compare it to F and see what's the same and different. That this code up here looks the same, right? And then down here, so that this is W as two variables, and then we're going to start to do something different. And at the end, you're going to end up having something similar. There's the R, there's a similar L, a jump. Okay, so we can begin to analyze the while loop. And we've managed to go through another class and have just barely made it out of a for loop and into a while loop. It's 11:47, so class is almost over. So what we'll do on Wednesday during the class is go through the W for the for loop and look for the differences. And of course, you can do that too between a for loop and a while loop. And then we can add, we will add a function call to this program. And then we can so then we can go from there, maybe make a third one that will do a do while loop or whatever. But anyway, so you get the idea of what the control, I mean, what they're only going to be minorly different. So that they're basically minor variations on the same code, because all loops are these loops are really the same thing, doing the same thing at this level. Okay, so I think I should stop there. Make sure and save all these files so that then at the end you'll get the whole thing. Question? You mean you did this and you compiled it? Yeah, well, free you to head off because it's 11:48. But let me uh, get maybe if you want to share your screen. Oh well, let me since let me stop recording.